Can I have your attention, please? Welcome, everyone, to today's medal ceremony and the plenary lecture. My name is Sigurður Reynir Gíslason. I usually go by Siggi, and I'm the Vice President of the European Association of Geochemistry. Now, collaborating with other scientific societies is key to building a strong geochemistry community and a successful conference. Therefore, it is an honor to have 3 societies present their awards today. First, I would like to welcome Wei Dong Sung from the Zheng Sung Sung Foundation to present the Zheng Sung Sung Award.
Good morning, everyone. I'm Wei Dong Sung from the Chinese Academy of Sciences. At the moment, I serve as the secretary of the Zheng Sung Sung Foundation. The Zheng Sung Sung Foundation is set up to recognize outstanding young scientists under the age of 40, who works in mainland China, Taiwan, and Hong Kong, Macau. On behalf of the Zheng Sung Sung Foundation, it's my great pleasure to announce this year's Zheng Sung Sung Award goes to Professor Li Zhang from Center of High Pressure Science and Technology Advanced Research in China. Professor Zhang did a lot of work on ultra-high pressure stuff like post-perovskite phases. And her major contribution is to get the structure of very tiny submicron high-pressure products, during the diamond anvil experiment. You get a mixture of very tiny minerals, and her major contribution is to get the structure of those minerals. Professor Li?
Thank you very much. I now would like to welcome Michael Carpenter from the European Mineralogical Union to present the Research Excellence Medal. Please.
Good morning. My name is Michael Carpenter, and I'm here in my capacity as President of the European Mineralogical Union. The EMU Medal for Research Excellence is a solid silver medal which is awarded annually to a young scientist who has made significant contributions to research and who is active in strengthening European scientific links. Sylvie Demouchy is renowned for her scientific leadership in experimental geochemistry and mineral physics, for her scientific breadth and her extensive service to the academic community. And it is my privilege to present the medal, the EMU Medal for 2016, to Dr. Sylvie Demouchy.
And finally, I would like to welcome Thomas Meisel from the International Association of Geoanalysts to present the Young Scientist Award. Please.
Yeah, thank you, Sigi. So I'm Thomas Meisel, the president of the International Association of Geoanalysts, and the overall aim of our society is to serve the needs of the global geoanalytical community, and we do this in several ways. For example, by organizing international conferences. So please come to Sydney next year in 2018 to our geoanalysis meeting. We run workshops and courses like at this meeting here on Sunday. And we produce a variety of high-quality reference materials. And we also got a raffle prize, which will be you can win like 91,500 zircon, a very valuable reference material. And especially, in particular, by encouraging young scientists for as a future generation of our geoanalytical community. And we do this by awarding our annual award, this time to two young scientists. Young scientists in the sense that they did a PhD within the last 5 years or are doing the PhD. And one of them is Dorothea Machold. Please, Dorothea. It is my pleasure to award it to you. So, if you want to know more what black varnishes is, please come to her lecture tomorrow. And you find out, it says here tomorrow at 9:15, and you will find out how exciting work Dorothea did about varnish. If you haven't heard about that before, come to her lecture tomorrow. So, and the second award goes to Peter Onuk. Peter. Thank you very much. So, if you want to know more about Peter Onuk's interesting career and his interest in earth sciences and reference materials, please come to his lecture talk tomorrow. Thank you very much.
Thank you very much. Now to our plenary speaker. It is a pleasure and honor to introduce today's plenary speaker, Laurie Reisberg, the president of the Geochemical Society. Laurie obtained her BS at the University of Michigan in 1979 and her PhD from Lamont Doherty Earth Observatory in Columbia University in 1988. After postdocs at the Institut de Physique du Globe in Paris and at Lamont, she joined the CNRS in Nancy, France, where she is presently a research director. And it's interesting to point out that both the president of the Geochemical Society and the president of the European Association of Geochemistry, they're both in Nancy. There's a French conspiracy here, Laurie's specialties are radiogenic isotopes and highly siderophile element geochemistry. In the early part of her career, her work was centered on mantle geochemistry, including studies of formation and evolution of the non-Crytonic lithosphere and basaltic magmatism. She has also worked on erosion and now on how it is recorded in the marine radiogenic isotopic record, nucleosynthetic anomalies in meteorites, and the radiometric dating and source tracing of ore deposits, and most recently, of oil. As you know, the European Association of Geochemistry and the Chemical Society jointly run the Goldschmidt Conference, which is named after Victor Maurice Goldschmidt, a founder of modern geochemistry and a developer of the Goldschmidt classification of the elements according to the preferred host phases within the Earth into lithophile or rock-loving elements, siderophile, iron-loving elements, chalcophile, ore-loving elements, and anthrophile, gas-loving elements. There's a lot of love here. Laurie's talk will bring us to our Goldschmidt geochemical roots. She will talk about the iron-loving elements. The title of her talk is Highly Siderophile Elements, a Window into the Earth's Mantle. Laurie, please take the stage.
Thank you, Siggy. Good afternoon. As Siggy has mentioned, the EAG and the Geochemical Society organized the Goldschmidt Conference in alternate years. As a symbol of the growing cooperation between our two societies, the hosting society it's become a tradition for the hosting society to invite the president of the sister society to give one of the plenary lectures. And I'm greatly honored to have the opportunity to do this today. So before getting started, I'd like to just broadly thank everyone who's worked in our lab over the years, and most particularly two people, Catherine Zimmerman, our engineer and lab manager, and Christian Parmentier, our assistant engineer, whose contributions have been absolutely essential throughout my time there. So, as Siggy said, I'll be talking about the highly siderophile elements, which are iron-loving, as the name implies. I think it's a good time to be talking about them because there's been a lot of recent work done in this field, which culminated in 2 workshops within the past couple of years, and both of these have led to special volumes. I will be trying to sort of summarize and synthesize some of the constraints that highly siderophile elements place on how the mantle formed and functions. Now, I should say that this is really the result of the work of the entire community in some sense, that it's very much a group effort. On the other hand, we all have different interpretations in any discipline, and so what I'll be presenting should just be viewed as one person's current personal perspective and not any kind of consensus viewpoint. I'd like to start by considering just why are the highly siderophile elements so siderophile? Part of it is just obvious right away from looking at the periodic table. These elements underlie iron, cobalt, and nickel. And so this means that their outer electron structure is similar. On the other hand, 5 of these elements, oops, what did I do? Goodness. Let's go. Let's see the whole talk rather quickly now. 5 of these elements, I think I'll stick with this pointer so I don't do that again. 5 of these elements are extremely heavy. That is, they have masses between about 185 and close to 200. So how do they fit into metallic iron, which has a mass of 56? The answer comes by considering the elements that come before them, the lanthanide series. Now, these different colors here are because the periodic table can be divided into different blocks on the basis of the orbital structure of the highest energy electrons. So the HSE are all D block or transition elements, and before them, these green ones are F block elements. One particularity about F block elements is that when they're adding, they do little to shield the outer electrons from the attraction of the nucleus. So as the atomic number goes up, the number of protons in the nucleus goes up, and the attraction gets greater and greater, and the atomic radius decreases. This means that the succeeding D block elements start as atoms that are already surprisingly small. Now, at this point, I just want to thank Thomas Meisel for a lot of particular help he gave me with this part of the talk, including giving me some of his slides. So this shows atomic radius as a function of atomic number, and as I just said, the D block elements of the 6th period have just about the same atomic ratio as the 5th period. And this is because of the lanthanide contraction. And it also explains the extremely high density of these elements that fall in the 6th period, the osmium, iridium, platinum, and rhenium. Another consequence of the lanthanide contraction is that because of the small atomic radii, which are coupled with high atomic numbers, the HSE have high ionization energies and are resistant to oxidation. In other words, they're noble metals. So to sum up why the HFC are so siderophile, there's basically 2 reasons that both come back to the lanthanide contraction. their atomic radii are only about 10% greater than those of iron, nickel, and cobalt, and they have a tendency to form metals because it's very difficult to oxidize them. I should also say at this point that the HFC are also highly chalcophile, that means sulfur-loving elements, and this will become quite important later on in the talk. So I'm going to be talking about one of the HFC more than the others, and that's osmium. Osmium is it's the densest element because of this effect of small radius coupled with high atomic mass. But of even more importance to us, it has two partly radiogenic isotopes. One of these is 187, which is formed by the beta decay of 187 rhenium with a half-life of about 42 billion years, which is, to give you some frame of reference, it's 10 times the age of the Earth and about similar to the half-life in the rubidium-strontium system. The other is platinum, is osmium 186, formed by the decay of platinum 190. Now, as you see, the platinum 190 is an extremely minor isotope of platinum, and the decay constant is about 10 times longer than that of rhenium 187, which means that the isotopic variations of 186 are much smaller than 187, and so there's much less, far fewer number of studies have been done. So I won't be talking about that today, but fortunately there was an excellent talk on that subject by James Day a couple of days ago that I hope you had the opportunity to see. So here's some kinds of samples of the Earth's mantle. There's basically two types available. There are magmatic rocks, basalts, picrites, and komatites, which basically provide some kind of an imperfect average of large volumes of the Earth's mantle. On the other hand, you also have point samples, which are peridotites, and these are found in two basic contexts. They are found as mantle tectonites, big pieces of the mantle that are sort of pushed up onto the crust or exposed on the ocean floor, or they can be found as xenoliths, which are pieces of the mantle that are torn up in more rapid volcanism, such as kimberlites and alkali basalts. And I'll be concentrating on peridotites today. So with that little bit of background, let's talk about how the HFC behaved during the formation of the Earth. Now, since they're such highly siderophile elements, essentially all of the HFC should enter into the Earth's core during its accretion and during differentiation. They have metal silica partition coefficients of at least 100,000, perhaps higher. Now, this is very well known that, in fact, what you expect to see are extremely low concentrations and probably not chondritic ratios, but instead you see much higher concentrations and with flat abundance patterns. These are normalized chondritic abundances. So there's been two basic classes of hypotheses proposed to explain this difference between observed and expected. One is that chondrites have been added at the end of core formation, or at least that they haven't seen the core, basically they haven't equilibrated with the core. And the other is that the conditions of core formation are different from experimental conditions, so perhaps some of our experiments are not really pertinent. And if we change the conditions, we might be able to do it. Now, this is a slide taken by a recent review paper by Brennan et al. And what it shows is how concentrations and relative ratios of three of the HSE vary with temperature, assuming that pressure and oxygen fugacity are held constant. These horizontal bars represent the observed bulk silicate Earth concentrations and ratios. And you can see that there's no temperature of core formation that can explain the observed HSE abundances and ratios of the bulk silicate Earth. But you might say, well, that's keeping pressure and oxygen fugacity constant. What happens if you allow those to vary as well, perhaps allow some compositional variation? Can you possibly do it? And I think what we should realize is that perhaps you could come up with some way of doing it for the Earth. But on the other hand, it's not just the Earth that shows flat patterns. It's also Mars and the Moon. So while you can imagine coming up with, possibly coming up with some kind of combination of parameters that would allow no fractionation for the Earth, this couldn't be happening in all these very different planetary bodies. So I think this means that core formation, the HSA must have been explained by addition of chondritic material after core formation effectively ceased, or some other mechanism by which they never equilibrated with the core. Now, what could be the composition of this material? This is actually the third time I've seen this slide during this conference, and this sort of emphasizes what an important result I think this is. This shows nucleosynthetic isotopic variations of ruthenium, which is one of the HSE elements, compared to the Earth's value in various classes of meteorites. Nucleosynthetic variations basically reflect the differing mix of components formed in distinct stellar environments in a sample. And so you can see the particular mix that you find in the Earth is most similar to that found in enstatite chondrites. In some ways, this is logical because the enstatite chondrites are thought to be derived from the region closest to the Earth relative to the Sun. Now, the Earth is actually a bit more extreme even than enstatite chondrites, but it's the closest class that we have. So just to sum up here, when the Earth accreted, almost all these HSE essentially all went into the core. The HSE that we currently see in the mantle were derived from about maybe 0.5% of chondritic material, probably of enstatite chondrite composition, that was added after core formation ceased. And so now let's think about what happens when the continental crust forms. Now that depends a lot on the behavior of the HSE during the partial melting of the mantle. And the HSE actually have different types of behavior. Some behave in a highly compatible manner, global manner during partial melting. These are osmium, iridium, and ruthenium. You also have some that are sort of moderately compatible, rhodium, platinum, and palladium. And then you have a couple, gold and rhenium, that are in fact mildly compatible. As a result, the crust will have very low concentrations of osmium and very high rhenium-osmium ratios. And what this means is that over time, the osmium isotopic composition of the crust should evolve very rapidly and reach very radiogenic compositions relative to those of the mantle, which remains more or less flat or just grows much more slowly because of its roughly chondritic rhenium-osmium ratio. Now, you might think that since the crust is so extremely radiogenic, it must have had a major effect on the remaining mantle. But this can be shown that just by simple mass balance calculations, this can be shown that this is actually not the case. If you consider that the continental crust was extracted from the entire mantle, it can be shown that the change in the rhenium concentration and osmium concentrations will be less than 1%, and the change in the osmium isotopic ratio that develops over time will be really minimal. If you consider that the crust was extracted simply from the upper mantle, then in fact the changes are a bit larger, but it's still probably less than 1%. So basically, you can say that continental crust extraction had almost no effect on the average 187-188 ratio of the mantle. But I've emphasized average because, of course, the mantle is heterogeneous because it's constantly undergoing plate tectonic processes with oceanic crust that's created with very high rhenium-osmium ratios, which with time become highly radiogenic, and leaving residues with low rhenium-osmium ratios that with time will become much less radiogenic relative to the average value. And the extent to which these heterogeneity are preserved will depend on the interplay between creation and convective stirring back in. So here are some samples that come from the convecting mantle. Mid-ocean ridge basalts, MORB, are generally considered to be the best estimate of the average compositions for many geochemical parameters in the upper mantle. Now, the problem for osmium is it's extremely difficult to analyze the osmium isotopic composition of MORB because of their very low concentrations that you see here compared to those of peridotites. Now, there was a fantastic study by Ganoon and his co-workers back in 2007 that's sort of summarized a bit here, and they actually worked through, first of all, the analytical problems, problems of late-stage contamination, and also problems of contamination in the magnetic chamber, and finally used high sulfides with high osmium concentrations to come up with a reasonable estimate over here of what the MORB composition really is prior to all these contamination issues. And you see that the average peak is fairly close to the value that you obtain for the primitive upper mantle that we'll be getting back to later, how this estimate is derived. And you see that there is still a significant difference between this MORB value here and the peak that you find in abyssal peridotite whole rock data. Now, when you look at peridotites in detail, you find that the sulfide data tell an even more complicated story, but unfortunately I don't have too much time to go into that. But what I want you to really notice is that the MORB and the abyssal peridotites are not in isotopic equilibrium, and that they cannot just be complementary reservoirs formed after partial melting of pristine fertile mantle peridotite. So you might say abyssal peridotites, maybe they're unusual, but here are a couple other samples of mantle peridotites, ophiolites, and oceanial basalt xenoliths from Hawaii, for example. And you see they show the same peak, and all have a peak. The peak is somewhat less radiogenic than the primitive upper mantle value. Now, let's look a little bit at what this means. Here I have expanded, this is the figure that you saw a little while ago, and I've expanded the mantle region, and I'm comparing the peak value of the 187, 186, 188 ratio with the mantle evolution curve, and this gives us a model age for a minimum time of melt extraction from these peridotites. And I say minimum because this assumes that absolutely every drop of rhenium was removed at this time. And of course, that's not true. So in fact, the time that these experienced melt extraction was probably even older. There is a lot of debate about what exactly this curve should be, but I think it's very difficult to avoid, no matter what curve you choose, it's difficult to avoid the conclusion that all the samples we have, or the great majority of oceanic peridotites, have experienced extensive melt extraction before they ever got beneath the mid-ocean ridge in the recent times. So to sum up the global systematics, just to bring home the main points again, the HSE were derived from the minor addition of material that probably was isotopically similar to ensitite chondrites after core formation effectively ceased. Continental crust extraction had very little effect on the average composition of the HSE composition of the convecting mantle, but this mantle probably is still not homogeneous and has heterogeneities that are created by constant plate tectonic processes. And finally, oceanic peridotites are not in equilibrium with MORB, and most suffered partial meth extraction more than 500 million years ago. So now that's the big picture, and so let's switch now to the little picture. And more specifically, what are the phases that host HSE in the mantle? Now, if they are present, which is usually the case, the base metal sulfides, that is sulfides of iron, copper, and nickel, will be the main hosts of these elements in mantle peridotites. And these phases make up less than 0.1% of the peridotite, but contain more than 99% of their HSE. So let's look at what's going to happen during the during melting peridotite as these sulfides are melted out. So this is the sulfides being melted out. They're almost completely gone by about 15–20% of melt extraction. And what happens depends on the sulfide silicate partition coefficient. Osmium and most of the other HSE is extremely calcified, has a partition coefficient, a d-value of about 1 million. And so as melting continues and material is removed, the bulk concentration increases slightly. Rhenium, on the other hand, is considerably less calcified, even though it's still quite calcified. This means that its bulk partition coefficient is less than 1, and it behaves as a mildly incompatible element and decreases during melting, which means that the rhenium-osmium ratio will decrease as the fraction of melt extracted is increased. Now, this slide is rather complicated, so I'm going to take a little bit of time on it, but I think it's quite important. I gave a d-value of 500 for rhenium, but in fact, it depends on a bunch of parameters, and among the most important of these are oxygen and sulfur fugacity. Now, these two parameters do not vary independently in the mantle. They're actually linked by this heterogeneous equilibrium. Now, James Bernand did some very interesting work on this, and he showed how the d-value varies with this relative value of sulfur and oxygen fugacities. This parameter is rather frightening to an isotope geochemist like me, but basically what this means is that here you have a lot of sulfur relative to oxygen, and here you have just a little sulfur relative to oxygen. And also I want to point out that this trend is probably the most appropriate of the two trends for upper mantle conditions. And so he found this trend, and he also noted that, in fact, because of the limited range of FeO in silicate melt and FeS in sulfide melt in the mantle, then this parameter is limited to a rather small range. And so if you compare it to the trend line, you find that the d-value for rhenium is also limited to quite a small range, between about 400 and 800. And so within this entire range, rhenium is going to behave like a mildly incompatible element. So in other words, the FeO in the silicate melt and FeS in the sulfide melt fixes the relative sulfur to oxygen fugacity, which in turn limits the rhenium partition coefficient to a small range, and which leads to systematic, mildly incompatible behavior of rhenium during partial melting. Now that's, of course, a gross major simplification, but I think it's the first order control. Now, what happens when the sulfides are completely melted out of the residue? Well, right before that happens, you can get exsolution, as shown here in the study by Fonseca et al., of ruthenium, osmium, iridium alloy phases, and you can also get other odd phases that form depending on the composition of the melt. So to sum up HSE behavior during melting, most of them have very high sulfide silicate values, and so are retained in the residue as long as the slightest trace of sulfide is present. That is, they show highly compatible behavior as long as they're sulfide. Rhenium, on the other hand, has a lower d-value, which is limited in range, can't vary much because of the relative iron and sulfur fugacities in the mantle, and so should show mildly incompatible behavior during uppermost mantle melting. And finally, at very high degrees of melting, sulfide is almost entirely removed, and the HSE are found in alloys and other platinum group minerals. So we talked a bit about the suboceanic mantle. Unfortunately, I won't have time to talk about the Crytonic lithosphere, which is an absolutely fascinating topic, but there's no point spending 2 minutes on it. It's really interesting. Instead, I'll talk about the off-Crytonic lithosphere, which is a subject I've come back and forth to throughout my entire career. So Okay, this shows the crytonic and non-crytonic lithosphere, how it's distributed. Now, the crytonic lithosphere, of course, is thick, it's ancient, it has diamonds, so it's very exciting. But most of the continents are actually underlain by non-crytonic lithosphere. And the interesting thing about it is that you find surprisingly systematic relationships between osmium isotopes and various indices of melt extraction. Here I've used alumina, I'll be using it throughout the talk, as an index of degree of fertility. If alumina is high, that means that not much partial melting has been experienced. As the aluminum content decreases, you find that means that there's been higher extents of partial melting. And of course, these correlations are by no means perfect, and you don't find them everywhere, but they're quite common. And it's surprising because for other isotope systems, they're much more rare, and that's probably because strontium and neodymium and other systems that are commonly used are overprinted by metasomatic processes because they're incompatible elements. Now, this had been known for quite a while that there are correlations between osmium isotopes and aluminum, and Thomas Meisel et al. Used this to define or to estimate the osmium composition of the primitive upper mantle. Basically, what they did was they found these trends and compared the value at 4.2% aluminum, which is thought to be the chondritic value, with their trends, and came up with a quite well-constrained value for the primitive upper mantle. And as it turns out, this value they come up with is just a little bit more radiogenic than the value that you find, the average value that you find in the compilation of enstatite chondrites. It's much higher than the carbonaceous measure. And remember that earlier we said that from ruthenium nucleus synthetic anomalies, we found that the late accretion of HSC was probably derived from enstatite chondrites. So there's some consistency here, though it could be coincidental, of course. On the other hand, there's absolutely no evidence that truly primitive mantle have survived in the upper mantle. And in fact, if you analyze the samples that actually have ratios like that, for strontium and neodymium isotopes, you won't come up with primitive values in most cases. So what is this PUM ratio? Now, what is it representing? And so to answer this question, we have to understand a bit more the origin of these osmium isotope versus alumina trends that have been used to define the PUM. First of all, can it just be mixing trends? And I think this is one of the few times that you can actually just say no. Because you have suppose you start with depleted peridotite, and you mix in mafic magnas. You change the alumina a lot, you don't do much to the osmium isotopes because the osmium concentration is so low in these magmas, and so you get a field that doesn't come anywhere near the trend. So that was from some work I did a long time ago with Jean-Pierre Laurent, and I should have mentioned, so I'll come back to it. This was on some Eastern Pyrenean peridotites. And so another possibility is that, in fact, these trends are basically isochron analogues, which form by radiogenic ingrowth after melting extraction. Basically, the idea is that during melt extraction, both the rhenium, osmium, and the aluminum contents will decrease. And with time, you'll get an isochron in this space and an isochron analog in this space. Now, you might ask, why don't we just look at the isochron? Basically, because rhenium contents are very frequently perturbed by processes related by processes related to the factors that bring these samples to the surface. So you often find much better osmium aluminum concentrations than true isochrons. Now, this seemed like a nice, simple story. But of course, simple stories just don't work in geochemistry in the world. And in fact, the problem is that peridotites are not simple melt residues. And this has been known for a very long time. This comes from an old paper from Fred Fry et al. And what they what they remarked is that the linearity of the major element abundance trends is surprising. This shows major elements plotted against magnesium content. And so they found lines, and you should find, at least for the more incompatible ones like sodium and titanium, strongly curved trends. While this has usually been explained by various degrees of melt retention during the melting process, but within the past 10, 15 years, it's been realized that, in fact, referralization of highly depleted peridotite plays a very important role and might explain the great majority of the laserlights we see. This is from a paper by LaRue et al. In 2007, who presented structural, textural, and geochemical evidence of referralization. So most laserlights we see are probably not pristine, but actually formed by referralization. Now, in terms of osmium, how does this work? And the question that arises is, are we talking about referralization or something that Rudnick and Walker described as auto-referralization? Referralization implies that would happen long after melting. So the idea is that you have ancient melt extraction, you let hundreds of millions of years go by, and then to get from here to here, you have to add both alumina and radiogenic osmium to get this kind of a trend. In auto-referralization, the idea was that melt extraction and readdition of rhenium and aluminum were practically simultaneous, or at least came very soon after the extraction process. And so you start with a range of values, which with time grow in a trend. Now, I think we can in fact distinguish between these possibilities, and that's because if you're talking about getting from making the trend by adding both radiogenic osmium and alumina, clearly the samples to which you've added the radiogenic osmium should have more osmium than those that you start with. So you should have a trend basically like that. But what's seen in almost in all cases is that you have flat distributions. You almost never see a positive trend that would be expected. And this, for reference, is what you'd expect from partial melting. You'd find a slightly negative trend like this, which also is closer, but is never really observed, or very rarely really observed either. So I think we can rule out late referralization as an explanation for most of these trends, and instead think of some kind of an auto-referralization or referralization around the time of melt extraction. And in a way, this is not too surprising, the fact that you don't find doesn't work, because osmium and aluminum should not be behaving in a similar manner and should not be added together. So what I'm suggesting as a possibility is that ancient melt percolation. Now, the idea here is that you take a Harzburgite and you let melt percolate, and as they percolate to crystallize various phases, pyroxene and spinels, and the crystallization of these phases will bring the sulfur content of the melt above the sulfur saturation level. I forget the word for it, I blank. So sulfides will saturate at this point and will take with them the chalcophile elements. Now you see, since osmium is such an extremely chalcophile element, it's not going to move at all. It's going to be precipitated, and the first sulfides that precipitate are going to sort of scoop up all the osmium that's in it. So the osmium is just not going to move higher up in the column. On the other hand, rhenium, because it is less chalcophile, will move up more rapidly. And aluminum, which is not controlled by the sulfides, but is controlled by the spinels and the pyroxene, will also move up at a roughly similar rate. So the rhenium-osmium ratio, because this is remaining stable, is also going to follow the same pattern. So what this means is that you're going to develop correlations between rhenium, osmium, and alumina with time because of melt percolation. And if you let these sit for a couple billion years, you can very well match the data that we see, for example, here in the Eastern Pyrenees. Now, another nice thing about this model is that the osmium doesn't budge. So the osmium concentration remains constant with alumina, which is what is observed. Now, I should say here, the most critical parameter in this modeling is probably the partitioning coefficient for rhenium. And as we noted, that this is fortunately constrained by the fact that the relative sulfur and oxygen fugacities in the mantle cover only a small range. So what do these trends mean? What does the PUM value mean? And why do these trends intersect at the PUM value? I think it's a combination of two factors. One is that continental crust extraction did not change the average mantle osmium isotopic ratio. So this could mean that extensive partial melting is going to roughly homogenize the osmium isotopic composition of the residues to something probably close to the PUM value, assuming that there hasn't been tremendous large-scale creation of differences between the upper and lower mantle. So you're probably going to have start with something close to the PUM value at the time of melting. And no matter what model you want to use, you're going to have this kind of homogenization at the beginning to get some kind of trend. And the other factor is the limited range of the relative oxygen and sulfur fugacities, which restricts the rhenium sulfur silicate partition coefficient to a rather small range. And this in turn is fixed by the FeO content of silicate liquids and the FeS contents of sulfides. So as a result, rhenium and alumina have similar compatibilities, so they're going to be added in approximately constant proportions during melt percolation. And with time, they're going to move up here. So, so even if you don't have an actual sample of this, the extrapolation of the trend, when you grow the trend in with time, you're going to have a point at about 4.2 that lies near to what the PUM value is. So I think that probably the PUM value may have some meaning as really being what the primitive upper mantle would be, but the samples that seem to have about the right composition are not actual samples of undepleted or unperturbed primitive mantle. So it's sort of a bit of a paradox that I think this value is probably meaningful, but we're not actually looking at samples of primitive upper mantles themselves. So just with that, I'd like to say there's a tremendous amount of work being done by the HSC community. An important part of it is trying to reconcile the extreme heterogeneity and extremely complex behavior that you see not only in different types of sulfides, but also in all these different types of PGM, platinum group minerals, with the much more systematic behavior that you see on a bulk rock scale. So that more work needs to be done to reconcile this difference. There's also an investigation, continuing investigations into many, many aspects of HSC mantle geochemistry, from the Crytonic lithosphere to the ancient Earth to the deep mantle, and also another important part is subduction mode processes. And finally, the application of highly siderophile elements, osmium isotopes, to other domains of earth sciences has become more and more important in recent years, and ranging from surface processes all the way over to the generation of petroleum. Thank you for your attention.
Well, thank you very much for your excellent talk, Laurie. Do we have any questions from the audience? Please go ahead. Do we have microphones? You can just shout.
Laura, as you know, there's a fairly good correlation between the composition of mid-ocean rich basalts and mantle peridotites in large areas of the oceans, the Azores, the southwest Indian Ridge, where alumina is correlated increase as well with increasing the fertile basalts. That has always been taken as confirming the complementary nature of residual peridotites and abyssal morb. We've been arguing lately that the Southwest Indian Ridge, there's no correlation between crustal thickness and the residual mantle and the abyssal and the morb. This would and that is really, we're looking at an inherited depletion, and so you're getting refractory basalts from refractory peridotites. This would seem to confirm that we're actually looking at when we're looking at systematic variations along the ridges, systematic variations in mantle composition, at least along the Azores and along the Southwest Indian Ridge. Any response to that?
I think it certainly could be part of that. I didn't want to imply that the abyssal peridotites are completely unconnected to the formation of morbs, but just that they're not the whole story.
I would certainly agree.
And so just that I think in certain cases you may have some kind of connection and others not, but I think you just have to be more, what can I say? You have to look at each thing on a case-by-case basis, but in general, you have to just take into account the fact that you just can't use a fertile peridotite as a model and divide it into a morb and a abyssal peridotite, as of course you know. I don't know if that answers your question much.
Well, it doesn't contradict anything that I said, which
No.
is that we have large variations in the mantle composition out in the oceans, and these are reflected in the morb,
Yeah.
and that these are inherited.
Yeah, that could definitely be the case.
So I have a follow-up question also related to, well, a little bit to the abyssal peridotites, which is following from what Henry said, that we see a lot of evidence in the abyssal peridotites for melt addition, some amount of the melt getting frozen in. So that would agree very well with the model that you presented in that last section of your talk for the melting followed by immediate melt addition playing a role in what you're seeing in the off-Crytonic peridotites. So then my question is whether you've made predictions about what should happen with the lithophile radiogenic elements such as strontium and neodymium, and if you can reconcile this model with those isotope systems.
I think with the lithophile elements, they're so easily overprinted, and it's you very frequently see later processes, so that I'm not sure that you would see the traces of it in most cases. I have to think a bit more about how exactly it would fit into the modeling, but it's clear that there are later referralization processes that don't do much to the osmium isotopes because the osmium is so compatible. But on the other hand, the neodymium goes all over. But I know that in Rhonda peridotype, for example, the neodymium isotopes give similar model ages, but seem to have been moved around recently. So it gets complicated, but you'd probably be able to trace this, and certainly it's something that's been done. Modeling of melt percolation models have been done, but I'd have to think about more what the effects over time would be, and the effects certainly of later referralization, later metasomatic overprints.
So essentially, if you're decoupled from the other lithophile elements, this would still work because I agree, there seems in a lot of these older peridotites to be multiple evidence for multiple episodes. And so if you can put in multiple episodes, then you could reconcile all systems. Okay.
Yeah.
Thank you.
Thank you.
Any more questions? Well, Laurie, thank you very much for your excellent contribution. And that concludes the plenary session today, and please go out and enjoy yourself.